Good morning and good day, everyone. My name is Tony. I'm a course advisor, and I will be your host for today's webinar. Before we start, I just want to also just put in some few housekeeping rules. So on your screen now, these are the notification and sound settings. So if you want to then switch on and off your notification and sound, you can do so during the course of this webinar. And also, please post any question under the Q&A function at the top right-hand corner. You will see it. So there will be a Q&A at the end of the webinar. So you can just put the question there. If it's technical questions, our presenter for the day will be able to assist regarding that. And these are some of the frequently asked questions. So everyone registered for this webinar will receive a PDF slide and a link to the video recording within the next 2 business days via an email. So please do make sure that you check your junk folder, spam folder, if the email does not appear in your inbox. And another thing is that we will provide a free digital certificate of attendance for live attendees, and there will also be a QR code and a short survey at the end of the session. So please do stay with us until the end of the session to qualify for that. Just a bit about ECT. So ECT is affiliated to the well-established Engineering Institute of Technology, EIT. So it's an engineering specialist which offers or delivers rather bachelor's and master's degree programs. Our programs are designed by industry experts, ensuring that you graduate with the cutting edge skills that are valued by employers. And ECT offers degrees to students from anywhere in the world, basically then. And also our lectures and our teachers are subject specialists with industry experience and the requisite academic qualification on online platform that allows ECT to source them from a large global pool of expertise. And we also do have a unique delivery mode. We deliver our programs via unique delivery methodology that makes use of live and interactive tutorials where you are able to also record the live sessions and go through it at your own time. And today's topic is 6 easy pieces of physics as applied to engineering. And our presenter for the day will be Dr. Steve Mackay, the Dean of ECT. Dr. Steve, you can take control.
Thanks so much, Tony, and happy to be here. Fantastic seeing everyone here. Thank you very much. I just want to make sure I don't make any mistakes here. And we've got a very good program ahead. Just want to make sure my drawing tool is working. Tony, I'm just going to scribble on this a bit. Yep. Okay, you can hopefully see that. And I'm just going to kill off my chat so I can get a bigger screen. It's always a problem with screen size here. Let's go. Okay, that's great. Okay, so we've got quite a lot of people joining. And Tony, I just want to confirm that you can hear me okay. You've got me.
Perfectly.
Excellent. Okay, that's brilliant. Okay, and hopefully everyone there can hear me. What you can do is put a comments in the chat box, and we can then respond. So there's a little chat box there as well. You can put comments in as well. So that makes it a bit more interesting. I won't be looking at the chat box all the time, but Tony will be. So I just need to have the screen available for me to use. Now, what we've got is a very detailed program of like 100 million slides. There's about 90 slides. It's far too many to cover in the period of 45 minutes because I also want to squeeze in a quick demonstration of one of my pride and joys, my love, which is Python and engineering. Now, Python's not a snake. It's actually an incredible programming package. And of course, today with AI, you can write all your programs in a matter of minutes. And someone like Tony here, who's probably more in the marketing side, the business development side, can also write a incredible engineering application using AI. So you do not need to be a hyper expert at the topic. So I want to demonstrate that right at the end. There's a few risks with my presentation because I'm presenting today. I'm actually at the tip of Africa presenting. So I'm halfway between England and Australia. We're normally based in Australia, and obviously we want to make sure you get the best here. So I'm going to be going very quickly through the key slides. All the slides, all 90, 100 of them will be available to you, plus all the Python programs as well. So I would encourage you to use them, to interact, and we can take it from there. My focus, as you would know, is practical engineering. I'm an electrical, mechanical, and chemical engineer. I love learning, much to the chagrin of my darling wife, who I keep up at 5 o'clock, 6 o'clock in the morning. And I really have a curiosity for engineering and life. So really, hopefully I can give you some of my joy in physics in this presentation. So what we're going to be covering today is atoms in motion, which most of you would be aware of, basic physics, physics and the other sciences like psychology, uh, geology, conservation of energy, theory of gravitation, quantum behavior, and then right at the end, the last 15 minutes, I want to do some demonstrations with Python. There's an element of technical risk there because Teams isn't quite there for presentations. Bless Microsoft. I'm not running them down. They've got a fine set of products. And what I'm doing this whole presentation around is Richard Feynman. He was one of the most amazing physicists and a bongo drummer, I might add as well. Amazing physicist in the 60s and 70s. And when I started my career in engineering, he was spoken about there with his red books. You may have heard about the red books from Richard Feynman. Anyway, he wrote this lovely little book on 6 easy pieces. So I took the key parts of it, put it into AI and said, hey, mate, create some PowerPoints for me, which is what I've got here. There's a few little errors in the PowerPoint, so I'll point out I'm not that happy with, but I'll point them out when we get to them. So he wrote a thing called 6 easy pieces. Very, very clever guy. This Richard Feynman is one of the best, should we say, instructors in physics to date. He's an amazing guy. There's a few others that say they're better, but he was an amazing physicist, and he was a winner of the Nobel Prize in physics. So he's no fool. There were a few little probably missteps he took in his career, which I'm not going to discuss here, but generally extremely clever man, a dedicated teacher, one of the outstanding physicists that we've got. And I really admire him in terms of his knowledge of physics. So really, the introduction to physics is going to be an introduction to scientific thinking. It's a vast field. It's a field I'm passionate about. And obviously, we have to use a lot of experimentation, and we need a very structured approach with the experimentation, and we need to be thinking about refinements all the time. That's really important. So as you're aware, I'm going to go through atoms in motion, basic physics, physics and other sciences, conservation energy, gravitation, quantum behavior, and quantum behavior. Hopefully I can demonstrate to you, and we can have a few debates. And with gravitation, we're going to talk also about the traditional gravitation, but I also want to perhaps throw open to you the issues of dark matter. Maybe we can talk about that if we've got a few moments. So really, scientific laws are approximations. We have the atomic hypothesis, which has been around since the Greeks. Democritus was one of the famous Greeks who actually postulated there's atoms that construct the universe. And obviously, we constantly refine those. So that's the story of physics, this constant refining of stuff as we come through. Atoms and perpetual motion and molecular behavior. I've got a really great little demonstration using a Python demonstration, which I'll do at the end. And we can, if we've got time, we can change the number of atoms to show the change in pressure. Obviously, gas pressure and temperature, that's obviously a really key driver for us in engineering. Um, Gas molecules move in all directions. And obviously, if you increase the number of molecules, you increase the pressure and more collisions. And obviously, temperature also can be a big impact. And obviously, compression, if you compress a gas, it increases the temperature. I'm told that's not a correct statement. It's only when you don't transfer the heat out. So obviously, it's done very quickly, and then we'll have a temperature effects. Solids, liquids, and melting. Obviously, the other point to make is that the building blocks are obviously solids, liquids, and ice structure. And obviously, the other thing is helium is an exception. It never freezes, even at absolute zero, which is quite amazing, something I never knew. And then, of course, evaporation and condensation. If you've got water vapor in the air, it's always present. Evaporation, molecules are moving up, and then you get condensation where the molecules, vapor molecules, move back into the liquid. And of course, you have equilibrium, which is a critical part in physics, often mentioned, where you have evaporation and condensation balancing out. So these are all important basic concepts in physics. Salt dissolving crystallization. Again, this is moving into chemistry, so I won't spend much time on this. I just want to go through the key concepts now. Chemical reactions and burning. Again, this is more in chemistry, but obviously we have the debate between chemical and physical changes. Obviously, carbon burning, oxygen levels matter. You could end up with carbon dioxide or carbon monoxide, depending on the level of oxygen in the atmosphere. And of course, there's a discussion now on molecular structure, atomic hypothesis. Obviously, we have chemical names. There's always a bit of a debate about the evidence of atoms. We can't really see them directly, although that's not quite true. With instrumentation today, there are some effects. And then Brownian motion is a random jiggling. I'm going to demonstrate Brownian motion with a Python program right at the end, and that shows you that there are atoms around knocking things around. So I'll come back to Brownian motion at the end. And then obviously the critical building blocks of physics are the scientific method, which has got three pillars, as we say: observation, reason, and experiment. And that constant process of refinement, experimentation, we learn new things all the time. And sometimes we go down alleys which perhaps don't end up anywhere. Area which I won't talk about today is things like string theory. Now, that's a particular theory in physics. It may end up in a cul-de-sac, a termination point, hopefully not. There's a vast number of atomic interactions, and they obviously create complexity beyond complete prediction. And we obviously want override. We're obviously hoping that we will see one theory that covers everything. And obviously, as you well know, we haven't got to that point at all. There's not one theory yet. And obviously, as I said early on, we're constantly testing and refining the rules. And obviously, the idea with physics is we're trying to understand nature's complexity using fundamental principles so we can describe everything. That's the driver. And you can look at physics as a game, simplicity and complexity, and testing methods where we can verify rules through direct observation, looking for patterns and approximation. And obviously, we're trying to look for the rules of nature. That's obviously the big thing, and we want one rule to describe everything. And that's obviously what I'm talking about now is Richard Feynman's concepts from his book. And obviously there's been a lot of amalgamation of physics and science. So we had in the early days, historically, we had mechanics, magnetism, optics, heat. They're all separate little disciplines. And obviously we've now unifying them into the physics field. And for example, which is pretty unbelievable, we've obviously linked up electricity, magnetism, and light. I mean, that was an amazing achievement from people like our friend in Aberdeen, Maxwell, and obviously trying to link magnetic theory, electromagnetic theory with light, which is quite unbelievable. And even then, in the 1890s, predicting the speed of light in those days. I mean, absolutely amazing research, Clark Maxwell. There's obviously a lot of things with forces and atomic interactions. There's 92 types of atoms. Those are naturally discovering. You would know that there's a lot more atoms, which we've got types of atoms, but those are the natural ones. And then obviously electrostatic forces and a force balance. And obviously one of the drivers of physics is the idea that we've got the atomic nucleus, and then you've got electrons sort of circulating around. But as we will discuss later in this presentation, it's not an electron rotating around as we would normally think. With quantum mechanics, it's actually a probability of finding an electron at a particular point. And I'll come back to that point a bit later. And obviously there's forces which push like-charged particles apart, but there's some amazingly strong, powerful force which ties the nucleus of the atom together to prevent it exploding, to breaking up. So we have electric fields, magnetism, electromagnetic fields, and we're going to talk about those shortly. And the atomic structure, well, obviously have protons and we have electrons orbiting around it. That's not quite correct. We have electron cloud, which has a probability of electron being found in a particular point using Schrodinger's wave equation. And again, one of the challenges with physics is that a particle is not necessarily a particle, it's also a wave. So we need to think about that duality of particle and wave, really important. Electromagnetic force, and this is one of the most amazing things, is that the electromagnetic force is so much stronger than gravity. It is incredibly stronger. And there's some speculation that the force of gravity did change over the last billion years. But of course, that's speculation. There's no proof. And then the charge balance is that atoms are usually neutral unless they're ions, like we spoke about earlier on, when they've got a charge. And of course, we have the electromagnetic spectrum with radio waves, gamma waves, violet, visible light, higher frequency act as particles. So again, we come back to this wave-particle duality, which I'll come back to in a tick, and the process of observation actually disturbing that particle of the point where the electron or the particle is located. And obviously the big impact is quantum mechanics with Mr. Einstein. And we'll come back to that in a tick with a bit more discussion about that. So the big thing which is causing a little bit of angst, obviously, is the wave-particle duality, which has been discussed for the last 100 years. So it's not old. The uncertainty principle, where we can't measure both position and momentum. In one of the slides, we put position and velocity. It actually should be momentum. And obviously, you can't have precise detail of both at the same time. And you have the issues there. And obviously, we have Schrodinger's equation to define that. So we have the uncertainty principle, and we'll come back to the tick, wave particle. And we have various nuclear forces and theories. The strong nuclear force, which obviously overcomes the electrical repulsion between protons, quite amazing, because obviously two positive charges you want to push apart. This force keeps them all stuck together. And there's an enormous energy, considerably more energy than a chemical reaction, which we spoke about there. And obviously you can classify particle types, baryons, mesons, leptons, and this is just a very short summary. We obviously haven't included all the particles there. And obviously, there's a lot of four fundamental interactions in the natural world: strong nuclear force, electromagnetic interaction, a weak force, and gravitation. So the strong nuclear force is very, very strong because it pushes the particles together. Electromagnetic interaction is considerably stronger than gravity. Gravity is pretty weak. And the idea is that they're all mediated by specific particles. So gravity, we always think about acting as a distance. Obviously, there's a suggestion that graviton is involved, but I'm not going down that track today. And obviously, the next question about physics is its interaction with other sciences. It has a huge interaction with other sciences. I'm just going to briefly look at those other sciences. Obviously, mathematics is the first one. And I suppose most of you probably would have come across Maxwell's equations. And I must say I was so gobsmacked when I came across Maxwell's equations because they described in exquisite detail in four equations written in the 1800s, described a complete picture of electromagnetic radiation. I mean, it's unbelievable. And as I said, also, that he worked out the speed of light. I mean, what an amazing person. And he invented some of the basic mathematical constructs, all described with mathematics. But mathematics is not a natural science because there's no experimental validation like physics. So it doesn't say it's not useful. It's extremely useful. Then we've got physics and chemistry, and obviously physics is very key part of chemistry. And obviously you get things like statistical mechanics, where you have a very probabilistic view of particles, and you have a very strong connection between chemistry and physics. Then we've got biology, and there's a whole thing with biology, and Feynman goes into quite a lot of detail here on biology. And probably one of the most important things with biology is obviously the Krebs cycle, which is where the cell breathes and generates energy, unbelievably and very incredible. And then we've got enzymes also, which obviously create the chemical reactions without being consumed in the process. So these are all sort of biology on the edge of physics, but physics is the thing. So, of course, Krebs cycle is often spoken about, and that's where we get our energy with the interaction with oxygen. And then, of course, we've got proteins in DNA, the blueprint of life. And again, these are all moving quite far away from traditional physics, but physics was at the beginning there. DNA, genetic information. And then, of course, astronomy and physics is an incredible impact. And one of the most amazing things is analyzing stars using physics, looking at the structure of the star, looking at black holes. Can anyone tell me what a black hole is? What's a black hole? Please tell me in the box. And thanks, Batet Samuel, for hearing me. I really appreciate it. Hi. What's a black hole? Anyone tell me? Black holes, black holes. Hello, hello. Anybody out there? What's a black hole? Just type it in the box. And it's something I'm not discussing in this presentation, but again, there's a guy called Stephen Hawking, Professor Hawking from Cambridge University, I think Vanessa, who spent most of his life speculating about black holes and horizons, natural horizons. Yeah, thanks, Vanessa. Brilliant. A region of space, everything is pulled towards it. So it's basically a star that's collapsing on itself, and it's got extreme gravity at that point, extreme point. It's almost a singularity in space. We never knew about it, but Stephen Hawking has fleshed out a lot of that stuff with the black holes. Then we've got geology and physics, another very critical area. And obviously, we look at the physical structure of geology. And probably one of the most interesting things with geology and physics is, of course, the fact that you've got in the middle of the core of the Earth, you've got a massive generator, a generator with swirling molten iron or nickel, not sure if it's iron or nickel, swirling around, creating a magnetic field. So you've got north up there, south there, and that field is moving as the molten core rotates around. So we've got a molten core at the middle of the Earth, and that's, again, the analysis is done with physics. And the other issue with physics and geology is obviously seismic effects. And obviously that disaster in Venezuela with the earthquake and huge number of people killed, whereas in Japan, a similar, not a quite the same size earthquake, but not as many deaths or casualties because they've obviously designed the environment to handle these issues with the seismic changes to the earth. So these are all big issues. Then, of course, we've got the very um, debatable issue here about psychology and physics. So, um, you know, it's a bit of a question mark there, but again, Richard Feynman brings it out and says, hey, let's talk about psychology as a science. And people would argue it is science. And there's lots of well-studied stuff with psychology. And then, of course, we've got all the scientific methods, understanding the brain and consciousness. And I suppose the nervous system's incredible complexity makes it difficult to reduce to simple physical principles. But can the mind be fully explained by physical laws? Probably not, I would say. But again, very interesting connection. So we can see the interconnection between the sciences. You've got the historical context, you've got cross-disciplinary challenges with all the different areas. And then, of course, we've got some questions about the fundamental origins. So we've got the connection of sciences. Now we're going to talk about conservation of energy. And obviously, this is probably one of the most fundamental principles in physics is that you cannot create or destroy energy. It's always there. It's time invariant. So momentum, you can have conservation of momentum, and that is space invariant, means when you move through space, it stays the same. With energy, it's time invariant, which means as time goes on, it is consistent. It doesn't, you don't lose or gain energy. That's really important. And that's one of the most important design principles when you're designing systems in engineering is that fundamental conservation of energy, critical building block. And then, of course, we have the old charlatans saying the perpetual motion, you can have perpetual motion. And again, energy conservation says there's no such thing as perpetual motion. You can't create energy from nothing, much as we'd like to. Then we've got gravitational potential energy and work. Potential energy is obviously weight, mass times height. And obviously, change in energy is the force times distance. Work is force times distance. Probably this would be better put into a integral, but we won't worry about that. And obviously, the point is always that energy is conserved at all times. And then there's a thing about virtual work, and there's different forms of energy: gravitational potential, kinetic energy, and probably the most common use of kinetic energy is half mv squared. Elastic energy, I've got a beautiful little demonstration of elastic energy and kinetic energy in a Python program, which I'll come to in a tick, which shows you the total energy stays the same, but the kinetic and the elastic energy changes with a spring. Boom, 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 boom. So we'll come back to that. And obviously there are other energy forms, chemical, electrical, mass energy, etc. And we'll come back to those in a tick. So the physics of energy and quantum mechanics. So now we're going to just talk a bit about energy transformations. It can change, and as I said, I'll demonstrate this in a little Python program. Heat energy, mass energy. You've got that very famous equation, mc squared, put together by Mr. Albert Einstein, and that means that your mass times the speed of light squared is energy, and that is obviously invariant. Energy is always conserved. And there are other conservation laws in physics. Conservation laws are really, really important in design for engineering. Thermodynamics and entropy, fascinating area. Energy is conserved, but sometimes due to entropy, you may find it's unavailable. Can anyone tell me what entropy is? What's entropy? Please put it in the chat box. Really important concept. Again, no time here to go into further, but what is entropy? In simple English, don't go too complex, but just simple English, what is entropy? Just put it in the box, please. Thank you. Any suggestions? Entropy. Yes, absolutely. Thanks, Victor. Disturbances in the system. So basically, the level of disorder is um, what we call entropy. And the universe itself, yeah, thank you very much, Patet. Brilliant, absolutely fantastic. Degree of disorder in the system. And the universe is going towards greater entropy or less entropy. What's the answer? Greater or less? Greater or less entropy? Who's going to take a chance here? You've got a 50% chance. Okay, the universe is tending to, yeah, okay, thank you very much. Yep, okay, great, thanks, Adulo. Yeah, great entropy. The universe is tending to move towards great entropy. Thank you very, very much. Absolutely right. And it's a critical part of all our design is entropy. Very important. Particle conservation, charge is conserved. That's another conservation. We don't really talk about it much, and certainly in engineering, I can't think of that being a big part. I suppose it's a electrical engineering problem ultimately. Angular momentum and linear momentum. So linear momentum, really, this is not very well put. Basically, linear momentum is invariant under space. It's space invariant. So that's where you conserve it in space. So source of energy and gravitation. Obviously, all energy sources originate from the sun. That's not quite correct. I wouldn't say all. Mostly, you'd say a large number of energy sources originate from the sun. We've got sources of energy in the ground, in the earth. Um, and obviously, this is a provocative statement designed to irritate anyone who doesn't think along renewable energy. Solar radiation far exceeds human needs. That's probably fairly true, but whether that's a solution to our energy problems is also a debatable point. And hydrogen, unfortunately, um, we used to run a lot of hydrogen courses, and I was very, very, very excited by hydrogen. The problem with hydrogen is the shipping of hydrogen is a problem. So you can convert it into ammonia, but you will probably be familiar with the problem that hydrogen had a huge amount of interest and it's dropped off a bit. I think ultimately, if we can get it right and get the costs down, it will offer a huge solution to our energy woes. But at the moment, most of the big entrepreneurs, the billionaires, have lost a bit of enthusiasm for it, particularly our friend in Australia, Andrew Forrest, who was really enthusiastic, put a huge amount of capital into it, but it's really hard to get that cost down. So let's hope that things will improve and we can get onto it. But it's very hard to push physics and research, engineering research, to go faster than people can do the research. It takes time to find new ways of saving hydrogen. But hydrogen does definitely offer a lot of opportunities if you don't have to shift it. Like making green fertilizers was one colleague of mine makes green fertilizers using hydroelectric schemes. So it does have opportunities there. The law of gravitation, obviously one of the most famous equations which we learned in high school. And this is put together by one of our sons of physics, Isaac Newton, and obviously there's the laws of planetary motion by Kepler, which again was an amazing breakthrough, although the church wasn't that impressed with him. Newton's law of gravitation, again, huge amount of beautiful work done on gravitation, and as I said, the inverse square law, which is really fascinating. And that is the square of distance between objects. The force is inversely proportional. Unfortunately, gravitation isn't as strong as, say, electrostatic or electromagnetic forces, but obviously it can be very important. And obviously the Earth's pull, we have the good old 9.8 meters per second squared is G, the force of gravity, gravitational acceleration. It's also really important. And then we have the Earth falling there, and we have tides, etc. And then the perturbations of the planets, Uranus, that irregularities in the orbit suggest another planet's existence, and that is basically due to the gravitational pull. So that sort of observation was done on an amazing breakthrough that to find another planet. And then we have galaxies, globular clusters. This is all astronomy, thousands of light years, probably I would say millions of light years. Thousands in many cases, but also millions. And then Cavendish's experiments, again, showing you that there's a lot of work done there with research from the 1700s. Gravity and simplicity. Again, here we've got the gravitational constant, which is worked out. And having a unified theory with gravity was good, but we still don't know what gravity is. And is it propagated by particles, gravitons? Big problem as to how we go further from there and how do you reconcile with quantum issues, which I'll talk about in a tick. So we try to explain gravity. And here's another question here. The electrical force is very strong. Gravitational force is very, very weak. So there you have electrical repulsion between two electrons to the actual gravitational attraction, 1 to 4.17 times 10 to the 42. What an amazingly tiny force gravity is compared to electrical forces. So, and this ratio raises questions about whether the gravitational constant changes the universe ages. Again, this is a very, very naughty speculative statement. Please forgive me. I don't think it's fair. There's discussions about it, but it's not, I wouldn't really humor that with too much thing. Gravity and quantum mechanics, a lot of work trying to tie the two together. The other little thing which is fascinating is gravity is not instantaneous. We always think about instantaneous. What I would like to ask you, what speed does gravity travel at? What is the speed that gravity travels with? And one of the most beautiful, beautiful Python little analyses I did a few years ago was to look at the gravity going through the Earth that is picked up in the Earth from a black hole implosion and actually analyzing the wave that went through. So my question to you is, what is the speed of gravity? How fast does it travel? Please put in there in the box. What is the speed of gravity? Yes, thank you, Vanessa. Absolutely right. So gravity travels at the speed of light. So there's nothing like, hello, it's going to be instantaneous. It travels at the speed of light. So when those black holes imploded and they went through the Earth, they had the measuring devices using gravity, using mechanical means to pick up the change in the actual gravity coming through, the gravity wave coming through. It was an amazing analysis. And if you haven't done it, it's something you should really think about, using a Python program to analyze that wodge of data to actually see those black holes that imploded. And the wave then came through the Earth. I mean, it was just surreal physics, surreal. And using big data, mass, lovely, huge wads of data. So there's obviously the need to tie it to quantum mechanics, which is a bit of a problem. Classical theory, as I said before, has failed at the atomic scale. So as things get smaller, classical theory works really well at the bigger stuff, but the smaller stuff, not so good. So we have particle waves, and these are really important. So they behave like particles. And there's a nice little demonstration I want to run through with a Python experiment, which is bringing us very close to that now, because we're going to run out of time. So obviously the idea is if you've got two slits and you think about a wave, electrons coming through that slit, that's the very famous experiment with double slit, and you find that the actual electrons, two electrons coming through the two slits, tend to interfere with each other. Now, it's impossible for two bullets or two particles to interfere with each other, so the electrons behave like waves. But as soon as you observe the electron, as soon as you try and observe which electron going through which hole, it immediately becomes a particle. It stops being a wave and it stops interfering with itself, almost like it's aware, hello, I know you're watching me, so I'm just going to behave like a particle. So that's a really interesting issue. And here's a comparison between bullets and waves as to what it is. And I'm going to run that little program, that Python program, in a tick. So we have constructive interference and destructive interference. The idea is that you have, when the peaks align, two waves align, you get a buildup, constructive. When the two peaks misalign, when the one peak is there and the other bit of the other wave is in the other direction, then they tend to cancel, destructive interference. So we'll come to that little demonstration in a very close tick. So we have electron wave particle duality, which means you can't describe a electron as a wave or a particle. It really has properties of both. So that's quite an important thing of quantum mechanics. And that is probably one of obviously the biggest changes to physics is this discussion of quantum behavior. And the challenge is to reconcile quantum behavior with classical mechanics like electromagnetic theory, theory of relativity, get those all combined into one unified theory, and obviously with the nuclear descriptions as well. So I'm going to just pull that together now with a electron demonstration with the demonstrations. I'm going to run through a few programs now. Tony, I'm going to ask you whether I can change to the
your other screen.
Yeah, I'm just going to just do a few more slides, and then I'm going to just swap over in a tick. So we have Heisenberg's uncertainty principle, which says you can't measure the physical position or the momentum at the same time. You can't get 100% description for either of them. So electron doesn't orbit a nucleus. It's actually just a cloud, and you have a probability of finding an electron in a particular place. And there's a very famous sort of riddle, I suppose, of Schrodinger's cat, which is always an amusing thing about a cat being left in a radioactive state, and the cat has a probability of being dead or alive. It's not dead or alive, but obviously that sort of paradox is not easy to think. And the other little point, as I said earlier on, is that the measurement initiate limitation, the active measurement changes the system being observed. So I'm going to run through these little demonstrations now. We'll provide these programs to you, of course. And obviously, there's an issue with the square of the probability amplitude. And as we said, you cannot predict electron paths with 100% certainty. Disturbance observation always affects the system, because as soon as you try and find out where the electron is by bouncing a photon off it, of course, that disturbs the electron, as you would know. So position, momentum, precision has a fundamental limit. So I'm going to just ask, there's a few risks with this demonstration, by the way, friends, and that is that the whole system collapses and we don't go any further. but I will try and run it through seamlessly and then we'll come back. So if something happens and you get booted out, please log back in. I believe we've got it all sorted out, Tony, haven't we? We'll
Ye-
we'll we'll,
Yes, I
we'll
think we
get this
should
right.
be.
We'll get this right. So I've got a few demonstrations now, so please forgive me. It'll take a bit of time to come up on your screen, but these Python programs are worthwhile trying out, and it's all free. You can load up the thing, and I'll explain how it all works. But you have to download a thing called Anaconda. Anaconda is the program, and that will actually give you the facility. And then you use notebooks, Python notebooks. You can probably even get the Python notebooks without downloading Anaconda. Unfortunately, Anaconda is about a gigabyte in size, gives you a huge amount of facilities. I'm only going to use one small part of it, which is the notebooks, and I'm going to run the programs there. So I'm going to run the programs, and I've got a few programs I want to run, and they will take a little bit of time, but I'll chatter around them. Okay, so Tony, if you can give me control, and I'll share.
Yeah,
Share, share. Okay,
you
okay,
do have
that's good.
control.
Thanks so much. So there we go. Share window and select all. Let me just get the orbital mechanics. Let me go to the first one I'm going to show is Brownian motion. Okay, so let's come back. Hello, hello. Okay, share, share, Brownian motion. There we are. Okay, so the first one I want to demonstrate is Brownian motion. So can you see this program here, everyone, good friends? Tony, can you see it?
Not on my side. I can only see your face, actually.
Oh, really?
Yes, I can only see your face now.
Um, can you see it now?
No, you can just try to stop sharing and try sharing
Okay, what
again.
can you see now? Can you see now?
I can only see your face on the screen, on the big screen. I'm not sure if the
Oh,
attendees, let me just ask the attendees if they're able
can
to.
you see Brownian
Oh, we can
motion
see the
simu
chat.
Can you see Brownian motion simulation?
Okay, they can see it, but the recording is on the recording is the screen, it's your face. So I'm not sure if you can
Oh,
stop sharing and try sharing again.
let me try again. Yeah, let me try again. Oh, yeah, yeah, I see that. Yeah, okay. So let me try again. Share. Uh, okay, what about now?
There we go. Yes, it's appearing now. Perfect.
Okay, everyone can see Brownian motion simulation. Can you see that, Tony?
Yes, I can see it scrolling down. I
Excellent.
can
Okay,
see it.
so the Brownian motion simulation is one of the first things I spoke about in the presentation. So I'm going to run this one here. This is trying to show you that every particle, this program has been written for me. I wrote it initially, and then I got AI to put it together. It can be done for you. And you can see here the result. It's a program written. It's a very simple program. And here's an example of Brownian motion. There's a little red dot. Can you see the red dot, Tony?
Yes, I can see the red
Okay,
dot.
brilliant. Oh, that's fantastic. It's working. Thank goodness for that. Okay, so you see the red dot running around there, and then you see the path of the of the red dot. So that is Brownian motion. It's a little random thing, and that's showing you that there's atoms bouncing around on that particle, moving it around. So that shows you Brownian motion. And this little program, very simple little program written, and it's got a little random seed there, so it tells you random, and it's trying to give you a random walk. But very, very easy to write, and even easier just to tell, hey, Mr. AI, can you please write a program demonstrating Brownian motion? Or I'll use Steve and Tony's program, this one here. Okay, so that's the first one. The next one is energy conservation. So can you see the energy conservation is the next one? Tony, can you see that?
Yeah. Yes.
Energy conservation. Okay, so this is the next one. So now this one here, I want to show you a spring mass system where the energy stays the same, but the kinetic and the potential energy bounce around. So let's have a look at that. So just give me a few moments. It's got a little bit of data, so it takes a bit of time. Kernel connected, created. Please reset kernel. There we go. Okay, so there the kernel starts. And it's, again, another very simple program with a spring mass system. And this simulates the energy flow for potential and kinetic energy. So here, look at this. So there we have the green is the potential energy. Can you see as the spring is going backwards and forth like this, the actual potential and kinetic energy change. So as the spring pulls together, you've got maximum potential energy, and as it's moving out, of course, the kinetic energy, it starts speeding up, F equals minus kx. But the total energy is constant all the way through. It stays right there. Woo, woo. No change at all. So again, a beautiful little demonstration. Let's look at the next one. Orbital mechanics and gravity. Can you see that one, Tony?
Yes.
Sorry to
I
pick
can
on
see
you
it.
like this, Tony.
Not a problem.
Okay, so now we've got orbital mechanics, and this shows you how different launch speeds, and this is due to gravitational effects, how objects' trajectory affect here. So this one's already just done the calculation here. So what you can see here is the blue, which is a very low speed, 0.5. And as you can see, it's been fired at this point here, and it can't escape the grasp of that object, the central mass. That's gravitational force pulling it. Then we fire it at a slightly higher speed, 1, and of course it goes a little bit further around, so the orbit's a bit bigger. And then we fire it again at a higher speed, 1.41, and again it goes further away. And then eventually we have the Elon Musk mission to Mars, where it actually escapes the gravitational pull of that central mass there. So that, again, a beautiful little program to demonstrate that. Very easy to run, very easy to install. And of course, you'll see here the actual equations there, square root distance, and of course, the actual working out the escape velocities. So that's the one. And then the last one, atomic pressure and motion. I always love this one. Look at this beautiful little one here. Now this shows you how pressure rises from molecular movement. So we've got atomic motion pressure. So here we have, let's get this one working. It's not actually operating at the moment. I've probably overloaded my poor computer with all these little programs. I'm trying to run them as well as Teams, as well as all the slides, but let's see. So atomic motion and pressure, look at this here. It's trying to come up. Hello, where are you? It's coming up now. I'm trying to reset the program, but it's sort of frozen for some reason. Restart kernel. Let me just kill the other ones off. Only motion, leave that. Atomic. Okay, so this one should. Oh, for some reason it doesn't want to run. Okay, let's try that again. Okay, so for some reason it's not running. I don't know why. Okay, it says kernel starting, please wait. Obviously, it's, there we go. Okay, so it's running now. I think my computer's a bit overloaded. Apologies for that. So there we have gas particle motion in a box. You can actually increase the number of particles, But as you see the particles hitting the side of the wall there, and they create pressure. So the more and more particles we have, the greater the pressure. And again, a beautiful little program written, and it does the program, the actual particles in a random motion. So it's beautiful. Okay, so Tony, are you still with me?
Yes, I'm still here.
Excellent. Okay, now the last one is, I know we're running out of time, but the last one is the double slit experiment simulation. Now, this is where you've got particles being fired or two electrons being fired to two slits. Now, the first demonstration of this program, it's quite a complex program, is to show you then when you don't observe, you're not trying to observe the electrons, you're just running it. And this one will be, we'll run this one. Okay, kernel created, it's just setting it up, and you'll see it running now. So we've got two slits and we've got electrons being fired randomly through, and they will then create a interference pattern if you're not observing them. So let's observe this. It's going to run now. Just a bit overloaded, I think. Restarting kernel. Okay, here we go. Come on, sweetie. Quite a big program. I'll just run through it manually. So you can run through each step manually. There we go. Okay, I'll just run through it manually. For some reason, trying to do it all in one hit doesn't like it. So we run it through here, and you'll see here it's created, these particles are traveling through the slits, and you can see on the detection screen, a histogram there, an interference pattern forming, okay? So this is due to the fact that we've got a particle here, which is classical position. You'll see on this here, we've got a classical position. You'll see the interference pattern forming there, and we've got the electrons traveling through the two slits, and they're random, they're not being observed. And if we have the observer, you'll see a little variable here called, or a parameter here called the slit. So here we've got set title, where is it? Yeah, so you see here, observer on equals false. So this is saying there's no observer. Now, if I change this to true, that means there's an observer. This will change the whole way of that particle coming through. So can you see what happens now? Let's look at this now. Run, 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 run. So now we've got two separate manifestations of the electrons because you've got an observer looking at it now, and there's no interference between the particles. So as soon as you observe and you know exactly where the particle is, bang, it stops the interference. Remarkable, simple experiment. Okay, I think that's really it. I've run out of voice and time. I'd just like to stop sharing and hand the control back to my good colleague, Tony. I'm sorry to take up the whole screen there, Tony. It's a bit of a pest.
No
Can
problem at all.
you take me back? Can you take your slides back?
Yes, I'm going to take you back just now.
Yeah, sorry, I've got the whole screen now. I'm sorry about that. I don't know why I took the whole screen. That's a bit of a pest. Anyway, can you get rid of me from the screen? Oh, there we go. That's good. Thanks. Thanks so much. Okay, so thank you once and all. Very much appreciated for listening into my ramblings. And really, thank you so much for your contribution, everyone. Really appreciate it. I don't know if there's any comments or. Oh, yeah, you can see it. Thanks, Richard. Thank you, Adulo. Edward, yeah, sorry. There's a little bit of a challenge with teams running these demonstrations. It's not quite suited, but I think Microsoft are working on it, making it a bit easier. But thank you so much for participating and getting involved. Really appreciate it. And there'll be a full recording, and all the programs will be provided to you. Um, and you can easily set up these demonstrations yourself, and you can do any physics exercise now with Python, and it's beautiful. I mean, and AI will explain to you, write the program, you can critique it, say, mate, sorry, this is rubbish. It is huge opportunity at the moment for what you can do. And just love, I just love this ability to take Python and get really realistic things. But I just want to say one final thing to you. With AI, do not trust it one bit. Always keep in your mind critical, hello, this doesn't make sense. But really, Python and Anaconda Navigator, which you can download for free, as long as you're not running a commercial factory with thousands of products going out the door. Privately, you can use it, no problems at all. So thank you very much, Tony. And thank you, Tony, for shepherding me through this complicated stuff with Python online at the same time as the presentation. It was really good fun. Thank you very much, one and all.
Not a problem. Thank you very much, Dr. Steve. It was very fascinating, and hopefully the attendees also felt the same. Yes, so we are at the end of the session, actually. So on your screens, these are some of the topics that are covered by today's well, these are some of the industries that are shared that are covered by some of the topics today. So there is mechanical engineering, electrical engineering, industrial automation, instrumentation and process control, and there is civil engineering. For more information, you can just visit our website and we'll be able to assist you further. And these are the upcoming courses. As you can see on the right-hand side is the course name. On the right-hand side, sorry, it is the start date and different intakes for the courses. And again, you can also check our website. Our course advisors will then assist you in anything that you need. And also we do have professional certificate, which is 3 months in duration. So these are more of if you want to upskill yourself in a certain area within the engineering space, this is the program for you. It's non-accredited. It's an upskillment course. So you can check on the website also, you'll find plenty of them. So on the screen is a QR code. You can scan your phone to claim your certificate of attendance. And I'll also be sharing the link now on the chat box. So please make sure that you claim the certificate of attendance before Saturday as it expires. So let me just share now on the chat. There is the link for the certificate of attendance on the chat box, and you can also QR code on your phone to claim the certificate of attendance. Questions? Well, I think it was very clear. Hopefully, the attendees think the same, have the same sentiments as me. It was very fascinating the presentation. Any last words from you, Dr. Steve?
No, I just want to thank everyone here for listening to me. I'm a bit of an old character and I have a love for physics, always loved it. And I'm just always so gobsmacked at how the mathematics can tie in so beautifully with the physics. But we've got a very, very long way to go with physics since the days of Richard Feynman. Richard Feynman was a remarkable physicist and a passionate teacher. He just loved physics to bits, but we've got a long way to go to find the unifying theory. And maybe one of you guys and ladies out there have got the know-how, the ability to tie the whole thing together and to bring it into one. I mean, one of the big areas which I haven't spoken about, and I've run out of time, is obviously this issue about dark matter in the universe. because we can't explain why the galaxies are accelerating in their departure from Earth, and that's to do with dark matter. But again, a topic for another day. But thank you very, very much, one and all. Really appreciate it. I hope you have a great evening and wherever you are in the world. And thank you for joining me in celebrating Richard Feynman and physics. I've got many more presentations planned on these topics. Thank you so much. Cheers. And thank you, Tony, for choreographing it with your polite demeanor, sorting out all the technical issues at the beginning. Thank you so much.
Thank you very much, Dr. Steve, and thanks to all the attendees for taking their time to join this fascinating presentation that was delivered by Dr. Steve. So we are at the end of the session, and I would like to wish everyone a good day, or enjoy the rest of your day. That's it, and see you on the next one. Bye for now.